Hey, welcome back to Programmer Story Hour with Uncle Bob, or JavaScript Jabber, as we call it every week. This week on our panel, we have AJ O'Neill.
Yo, 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 coming at you live from the Now with Plywood Paneling shed. Or, instead of drywall, I got some plywood from a friend who was dumping it.
Nice. We also have Dan Shappir.
Hello from Tel Aviv.
I'm Charles Max Wood from Top End Devs, and this week we have a special guest. As I said before, we got Uncle Bob here. So, Bob, welcome back.
Thank you so much. Good to be back.
So, I was going to ask you what's new, but I have to say Pearson reached out to me about reviewing Clean Code, a new edition of Clean Code. So it looks like that's going to be a thing.
Yeah, I'm in the midst of the final reviews of that now, so it should be going into production within another month. And then, that process takes about 3 or 4 months. So
even cleaner code?
End of the year. What's that?
Even cleaner code?
We can only pray.
Clean Code 2nd Edition. I tried to play with other titles, but the publisher was very adamant.
Yeah.
It needed to be Clean Code 2nd Edition.
I think it's easier to sell if you keep the title.
It's, yeah.
We're not supposed to. That's not the topic of our conversation, but I've got to ask. I mean, the clean code principles seem pretty kind of universal almost. So why do we need a 2nd edition?
Oh, heavens.
I did say story hour. Go for it, Bob.
For the longest time, I thought, I'm done. I've never done a 2nd edition of anything. Usually when I write something, I think, okay, I said it. I don't need to say it again. And for the longest time, I thought that would be the case with Clean Code. But the Clean Code became so controversial. There were so many misinterpretations and misrepresentations and, errors on my part where I said things that could be taken in the wrong way that I thought, maybe it's time to dust that thing off and see if there isn't something I would say differently. And then as I was doing that, I thought, there's all this new stuff. There's all this AI stuff. There's all these, Copilot and Grok and all that stuff. How does that play in? And besides that, there's languages that I should probably explore, like Go. And I thought, okay, fine. Let's do a top to bottom rewrite, incorporating some of the original chapters with a lot of changes and just a whole new bunch of new chapters. The overall message is, of course, the same, but the way I say it and the examples that I pose and some of the nuances have shifted a rather significant amount. So I'm happy with it. I also decided to add a whole bunch of other stuff like design principles and design patterns. And it's kind of like, okay, everything I've learned over the last 10 years, let's kind of funnel it into this book and see what happens. So that's why there is a 2nd edition. Not least of all of that is that my publisher said, you should write a 2nd edition. I thought, okay, probably a good idea.
Awesome.
You mentioned the fact that you cover additional programming languages in the new edition.
Yeah.
I'm curious in that context, to what extent does the choice of the programming language impact the meaning, I guess, or the consequence of the code being clean? Like, would you apply the same principles in order to achieve clean code in different programming languages?
And that is one of the points of the 2nd edition, which is that the programming language doesn't matter much at all. I'm going to show you an example in Python. I'm going to show you an example in Ruby. I'll do one in Clojure. I'll do one in Java. I'll do one in C. Doesn't seem to make an awful lot of difference. There are little quibbles that you can make. Some languages want the order of the functions inverted. If you're working in Python or if you're working in Clojure, they want low-level things stated before high-level things.
I hate that.
Whereas in Java, you can turn it around in a way that makes more sense. But overall, the message of the book applies to all of those languages. And in the second edition, I tried to demonstrate that by just changing language from chapter to chapter to chapter.
Yeah, I remember when
With the help of Copilot, by the way, because I'm not a Python programmer, so I fire up Copilot and I get a lot of help. It was pretty interesting to watch these AIs throw code at me that I could review and then think, that's maybe not so bad, or in more cases, like I think I could do better.
Very cool. We're looking forward to that coming out.
One thing that I hear is like the number one criticism that I hear, and I think this is not accurate, but I want to know. People say, oh, or you could do it Uncle Bob style and only have 3 or 4 lines in a function. Is that true, or is that just like a misquote or a perversion of something you said? Like, I know that a lot of demo code examples to do apps, whatever. Yeah, like you end up, if you were going to enterprise it, and then you're going to end up with a bunch of things that are 3 or 4 lines long that don't do anything meaningful. But what is your actual advice on function size or grouping of logic?
My actual advice there is to keep it very small. I like small functions, and how small? Well, 3, 4, 5, 6, 7 lines, something in that range. I don't like to see 20 lines. I don't like to see 30. The controversy is 2 to 3 lines. Everybody says, Uncle Bob says everything's got to be 2 to 3 or 3 to 4 or whatever number they quote, and that's an example of people who did not read the book.
In that context, though,
That's what I figured.
Some programming languages are more condensed than others.
Yes, there are.
I know that you like Clojure. Clojure is pretty dense.
Very dense.
So 3 lines of Clojure could probably achieve a lot more than 3 lines of Java. 3 lines of Java, 2 of those lines are open curlies and closed curlies.
Yep.
So you're basically left with 1 line.
That is
Java.
Certainly true. It is certainly true that Clojure is much denser than Java, and yet it is much harder in Clojure to make small functions. And that's just because of the functional style and the fact that you need to set a bunch of variables up front and then operate them at a lower place. And it's very hard to separate those things out as independent functions. So just a quirk of the language, you end up with larger functions in Clojure, even though the language is denser.
So do you have like a general rule of how to determine what belongs together? Because I think line limit, to me personally, I don't think line limit makes a lot of sense, because a line limit is arbitrary. Like for me, I don't like to use comments. I put everything in a variable. So if I'm going to do a mathematical operation where I'm going to, add days of the week and multiply by hours or whatever, I'll actually write that out line by line, so that instead of commenting, this is taking this to make that because this number is special, I'll just var special number equals, and that way the variables declare themselves. So a function that somebody else would have that would be, or a operation like I break statements down, right? So I don't necessarily find line numbers in of themselves to be meaningful, other than that you got to be able to see it on a page. Like when you're looking at a block of code, generally you should be able to see the whole block of code. If it extends beyond what you can easily see, or you have to make your font size really small, then it's too much context in the brain.
I've got these. I don't make my font size too small.
Yeah, but on the other hand, and I think that there's the general case versus the exceptional case, and this might be the exceptional case, but if it's like a parser, I often find that my functions are way longer than I like them to be, because it's like, well, 1 unit of logic for parsing this thing is just this much logic, or transforming. If it's like a parser or a transformer. Yeah.
Yeah, so the line limit is always the wrong way to look at it, right? It's just because it's not a line limit that you're really going for. And in the book, and in the new book especially, I read a whole chapter about this in the new book, but in the old book, the rule was a function should do one thing. And how do you know that it's doing one thing? How do you remove the objective or the subjective idea of what one thing is? And my answer to that is that if you can use the extract method refactoring inside a function to pull another function out of it, you probably should. And then give that function a nice name, and those two functions will then do one thing. If you can take one function and split it in two with extract method, then probably you should, and those two functions will be smaller, of course, and they'll both have nice names. That's
I
my
definitely would say
fundamental rule.
if you don't know what to name your function, if your function name is do stuff, you definitely need to break your function down.
I literally once had to refactor code that had init 1 through init 10.
Oh, gee. Yeah,
There you go.
but
That's useful.
but
They kept the line rule.
The thing that we're kind of circling around here, at least the way that I approach it, is I like everything at the same abstraction level for one.
Yep.
And so that's one rule that I follow, right? And so if I can say this takes these steps A, B, C, D, E, F, right? And I can name the steps. Then that's usually what my function looks like, right? Or my method or whatever. And then I have those somewhere else, right? And so then those break down the same way. They're just the next layer of abstraction. But then the other thing is that if I have some big long function like AJ's talking about with like a parser, usually there are different stages or steps or functionalities in there that I need to go through. And so I can break all that out too. And so in a lot of cases, I don't typically find very many cases in any language that I've written where I don't wind up with just some somewhat shorter method. The only time it gets particularly long is if you have a case statement. And I hate case statements because it adds a line every other time. If the case, then do this, case, then do this, case, then do this. Or if, else if, which is also gross. But beyond that, yeah, typically you can break it out into multiple functions.
prefer indirection over ifs and switches. By the way, we have a question from the audience. Clojure from Vinicius, I think I'm pronouncing his name correctly, I hope. Clojure developers value recursion more than any other. How does recursion impact clean code? Well, I think that Clojure developers don't have a choice except to use recursion if they want to create loops. One of the people you didn't talk about in your book, or a few people, were Church. And also, I forget the name of the two guys that created Lisp.
Oh, yeah, we're here to talk about we programmers and the history of programming. Go ahead and answer this question, Bob, and then we'll move on to story hour.
Well, I mean, Dan is right. If you're going to use a functional language, you have no choice but to use recursion. Recursion is the only way you can do loops in a functional language. How does it impact clean code? It doesn't. Good expressive code can be expressed either with iterative loops or with recursion. So there's no real impact there at all. The impact that Clojure brings to the rules of clean code is that the act of creating intermediate variables is very difficult to extract out into other functions. Because in Clojure, when you create an intermediate variable, it is in the scope of your function, and there's no way to get it out without doing some nasty trick like creating an atom or something. And okay, probably don't want to do that too often.
Because you don't want side effects.
All right.
Right. Yeah, I mean, you can manage those side effects by creating an atom and then making sure you don't overwrite the data that you stick in there. So in that sense, you probably could pull out those functions. And I've played with that technique a few times, but it's always ugly. So then I wind up with functions that are 15 lines long, and I look at them and go, boy, I wish I could pull these things apart, but there's no real good way so far in closure that I have accepted.
Also, at the end of the day, it's not about achieving, like you said, it's not like about achieving some magic number.
Yeah.
It's trying to make your, I guess it would be try to make your functions as short as possible, but no shorter.
Well,
Yeah. Well,
given the constraints of the language.
and it's not easy either. I think people kind of conflate length and complexity, or length and difficulty, and it can and can't sometimes. But was it Mark Twain that said, "I didn't have time to write you a short letter, so I wrote you a long one"?
It was
Right.
Voltaire.
It was somebody important, but
Yeah.
the point is that it takes a lot of time to get right, to really get things in the right place, so that you have something like that that's easy to put together in your head. Anyway, let's get into We Programmers. I think we did this last time when we were talking about your your other project, where we went off on We Programmers for about 20 minutes, and then it's like, no, we were here to talk about this other thing. So, which is great because it makes it fun to talk to Bob. But yeah, so I'm kind of curious as we get in. What's your favorite part or story or whatever of the book, and can you kind of give us a little bit of the story there?
My favorite story in there. Well, there's a lot of stories that I really like, but my favorite story in there might be the story of John Bacchus. Because here's a guy who was a complete ne'er-do-well. He didn't have a great family life growing up. Kind of dumped on school. Didn't care about school because he's too damn smart, right? And everybody knows that kid who was so damn smart that he didn't even try. Right? School was just so damn boring. The hell with it. And he got drafted towards the end of World War II. Fortunately, right at the right time, he got drafted, and the Army saw this this ne'er-do-well kid and ran him through an aptitude test, and it blew their socks off. And so they said, you need to become an engineer, and they put him into engineering school. Well, that was too boring for him. He did extremely well, of course, but it was too boring for him, and he just spent his time at nightclubs and stuff like that. And the Army goes, this right at the end of World War II, right? So the Army says, this guy's so damn smart, they put him into medical school. He could become a doctor. And that was a bit more challenging, and Bacchus kind of enjoyed it, but kind of didn't. And then all of a sudden the war was over, and he was out of the Army, and he just dropped out of the school and said, yeah, the hell with that. And he built himself a nice little Wi-Fi system. Oh, by the way, that's not Wi-Fi, hi-fi. Back in the in the 50s, a nice sound system for his record player. Still only half of the people in the world know what I'm talking about. He built that, and he dabbled around a little bit. Really didn't get any jobs. And then a friend of his said, you should see this really cool thing that's down in one of the streets of New York City at the IBM building. And he goes wandering over there, and he looks in the window, and at the IBM building, Thomas J. Watson, the guy who founded IBM, had put in the display window the world's second computer, big computer, right? The selective, I can't remember the name of it. This gigantic machine, mostly electromechanical, couple of vacuum tubes, paper tape everywhere. This massive machine fills the room. It's got this really cool front panel, a Star Trek front panel. Lights are blinking. If you go inside, it's clicking away like crazy. And Bacchus goes, oh, yeah, that's kind of cool. And he asks for a tour. And the person giving him a tour, I think, must have smelled something. I mean, Bacchus was in very informal garb, shall we say, but must have smelled something about Bacchus's intelligence, because the tour guide brought him up to the department head, and the department head gave him an aptitude test and hired him on the spot. And he became the project leader of the Fortran project that gave us the Fortran language way back in the 50s. That is one of the most interesting intellectual rags to intellectual riches stories in the book. It's a guy that you would never expect to do well at anything and winds up delivering this wonderful thing to the world at that time.
So I have to ask. I mean, it's the book. I've not read it, but I've read excerpts. I've not read it yet. Let's put it this way. But I've read excerpts, and I also saw some of the stuff that you put out. And there are there's a large number of amazing characters and crazy stories about them. How did you decide who to put in and leave out, and how did you get all the information about the ones that you decided to put in?
Um, it's how did I decide who to leave in and who to leave out? This old Bob Seger song, right? There were a few that were obvious that I had to put in. I had to put Babbage in because the book wouldn't even start properly without Babbage, and you have to put Grace Hopper in because she was kind of like the first. And if you're not talking about Turing, you're not writing a book about software history. So you got to have Turing, and if you bring in Turing, you have to talk about the mathematician Dave.
Hilbert.
Hilbert, thank you. I knew it was starting with an H. You have to talk about David Hilbert, and you have to talk about John von Neumann. So those were kind of obvious. That's an obvious progression. Mm. And then, why wouldn't you talk about the three authors of C? Why wouldn't you talk about Dennis Ritchie and Ken Thompson and Brian Kernighan? In fact, you're going to want to end with that one because that's kind of where modern history begins.
Yeah.
And then in the midst of all that, there are these milestones. And most of those milestones I just uncovered by accident. Like the whole story of John Kemeny, the father of BASIC. What an interesting story that was. No, everybody knows BASIC. Hardly anybody knows the story.
You're making an assumption that's based on our age.
Well, okay.
I have to tell you that I speak with the developers that I work with these days. And, sometimes the topic of what's your first programming language comes up, and I say BASIC, and they say, what?
Yeah.
Like, people today don't know about BASIC. I mean, maybe they do because of Microsoft, stuff like VBA, but other than that, they probably don't know what BASIC is. And you know what? That's not such a bad thing. BASIC almost spoiled me as a programmer.
Oh, well, you didn't write COBOL then, because that would have spoiled you as a programmer. Spoiled me as a programmer for a day or two.
Well, you know the story about Ellen Kay and Grace Hopper?
Please. Please tell me the story.
Well, I recall reading it somewhere that he was walking around the university. I guess it would be Stanford, I think. I may be wrong. Maybe it was Berkeley. I don't recall where he taught. But anyway, he sees a group of people, and he walks over, and it's because Grace Hopper was there, and they were like showing her around. And the story is that they introduced them, and they said, this is Grace Hopper. She created COBOL. And he said, oh, I'm sorry.
Yeah. I am not kind to COBOL in my book. I'm very kind to Grace Hopper because I think she was a remarkable person. But
oh yeah, for sure.
God, I hated COBOL. I spent about 3 months writing COBOL when I was 19 years old, and it was not a fun time for me. So I've walked away from that language and never looked back.
Remember what happened when COVID hit?
I thought you were going to go for Y2K. So no, what happened when COVID hit?
I still remember. I think it was the governor of New Jersey or something saying that our systems can't keep up and we're in dire need of cobalt programmers.
Yes. Yeah, I've actually heard that since. There's a lot of people talking about these things are all written in Cobalt. No, okay, fine.
Well, it's like any other project that I've worked on. We don't actually update it until it's breaking.
I think some of these are long past that point.
Yeah,
Well, look,
yeah, but they can patch it over and yeah. Anyway.
yeah. Well, she also invented the term bug, as I recall.
Yeah. Well, I don't know if that she invented it, but in her notebook there is a desiccated moth that she pulled out of the relays in the Harvard Mark I. And in the notebook it says this is the bug we found in the machine. So I believe the term actually came from telephony, maybe even 50 years before that. But she put it in a software notebook, so we can credit her with that. She was, however, responsible for creating the glossary of terms, one of the earliest glossary of terms in our industry. So she coined things like register and bit and breakpoint and a bunch of other words like that we
Yeah,
all
I'm back
know
in
and love
college.
today.
So again, how did you go about the research?
I have got like a zillion books. And so it's all secondary research. I didn't do any primary research. In some sense, you could look at We Programmers, bring the book out, We Programmers. You can look at that book as a literature review. Because I read really significant books about Babbage and about Grace Hopper and about all these guys, right? And then I tried to condense them down and pull out two things. I wanted to pull out the human side of the story so that programmers who read this could identify the character flaws that they see in themselves. And these people are replete with character flaws. And then I also wanted to pull out the deep technology. That's something that most of these books do not go into. So I had to do that research myself. So when they're talking about when they're talking about the UNIVAC 1, they don't really go into much detail. So I've got to pull all that information out and then describe, okay, programmers, this is what a UNIVAC 1 was like. This is how you programmed it. I actually put some UNIVAC 1 code in there. And I talk about the kind of code that Grace Hopper had to write in the late 40s and early 50s to get the Harvard Mark I to work. So I wanted the programmers who read this book not only to identify with the human side of these guys, but also to identify with the deep technical problems that they were solving. So there's this really interesting juxtaposition. I think it's interesting anyway. Interesting juxtaposition of these frail human people dealing with really difficult technical problems.
I'd like you to go into more depth on one of these. You mentioned like maybe the UNIVAC or something else where, it's just something that we don't even fathom that they had to just figure out.
Well, start with the Harvard Mark I. This was a machine that was built by Harold Aiken. Kind of conceived of it in the Navy. He was a Navy guy, sort of.
Maybe get some popcorn.
He talked the Navy into building the thing. He actually talked IBM into building the thing, and then didn't give them any credit for it, which was a real problem for him later on. But his idea was to create this calculator that could add, subtract, multiply, and divide numbers that had 23 digits. I think that was the numbers.
Oh,
These
wow.
numbers had 23 digits, decimal. No, this wasn't binary. And the digits were all held in these counter registers. And the counter registers could be addressed and moved into arithmetic units that could add, I think it could add 3 numbers per second, if I remember correctly. And it could multiply, and it could multiply in something under 10 seconds. So fast by the standards of the day, but impossibly slow from our point of view. This machine was programmed by punching holes in a 24-channel paper tape. And the 24 channels were broken up into 8 zones. And the zones were the register you want to take the data from, the register you're going to put the data in, and the operation you're going to perform on it. And those 8 channels were all binary, sort of binary. The programmers programmed this by identifying what holes should have to be punched in that paper tape. And they did that numerically. So they would write their code as 4, 3, 6. I think I got that right. And 4 meant punch the 4th hole in zone 1, punch the 3 hole in zone 2, punch the 6 hole in zone 3. That's how they would write their code. And if more than one hole had to be punched, they would write two numbers in that zone area. And then they would come up with this program that was line by line by line, just these numbers, these 3 component numbers. And Grace Hopper is looking at this. She was like the 3rd programmer in there and was immediately turned into the lead. She took over the whole thing. Had never seen a computer before in her life, had no idea what these machines were. Aiken threw her into the task and said, okay, for your first job, you have to compute the arctangent coefficients to 23 decimal places, the interpolation coefficients for doing arctangents in 23 decimal places, which took her a week. And she had to figure out how the machine worked and how to punch the holes. And of course, she didn't have dedicated time on the machine. So she had to steal the time when the other guys weren't as busy as they usually are. And she managed to get that all done. And she worked all this out. And she realized, and by the way, this is where the word code came from, because they were writing codes. It was these numbers. So they called it codes, the computer codes. And she was one of the first people to say, well, each line ought to have a comment on it. So on the coding sheets that they had produced, a mimeograph machine, and they would, they'd crank out and produce these coding sheets. She put in a column for comments. First person to ever do anything like that. They began to learn as they were writing the programs for this thing. And the kinds of programs they were writing were ballistic trajectories for artillery shells and the timings of tides in various places, very deep mathematical problems. And as they did one after the next, they started realizing that they were writing some of the same codes over and over again. And so they would take these little snippets that would do something, some task, some small mathematical task, and they would write them into their notebooks. And they called these transcriptions in their notebooks subroutines. That was their name for them. And then they would share this back and forth. They would share their notebooks back and forth and eventually created a library of subroutines, which were just these handwritten documents in a notebook style. And whenever they wanted to use one, they would go to the notebook, they'd look it up, and then they would transcribe manually those codes into their program. Of course, the register numbers had to change because in one case you might be using register 3, in another case you might be using register 8. And so when they wrote these in their book, they used the convention that all registers were 0 or based on 0. So they invented relocatable programming. Just out of sheer raw need. Eventually, the programmers would write the numbers, but they would hire people to do the punching. And then the tape, the long tape, and these tapes got pretty long, the long tape would go back to the programmers, and the programmers would verify the holes against the code that they had written.
Oh, man.
There was no jump instruction. There was no way to do a loop unless you put the ends of the tape together, and then you could have a loop, and they actually did do that. I'm not sure that's where the word loop came from, but they did make loops of tape. But usually what happened was that there was a halt instruction. There was an instruction that would stop the machine. And then on the tape itself, the tape was fairly wide, 24 channels, right? So on the tape itself, they would write instructions to the operator. If register 3 is less than 28, then go to, and there would be a mark on the tape where they would back the tape up to and run it again. So all of the loops, all of the transfers of control were manual. They couldn't be done automatically, which meant that the operators were always on call, always watching the machine, always repositioning the tape to try and get any kind of iterative process done correctly. That's just a glimpse of the horrors of the earliest of programming jobs.
One of my favorite characters that you also talk about, and I actually learned about him from reading the book about the Manhattan Project when I was a kid, is John von Neumann, who was an amazing intellect and person. Like you watch a TV series like The Big Bang Theory, and everybody's kind of amazed by the capabilities of the Sheldon character. Well, think about somebody like that, only doubled, but also highly social.
Yes.
He was well known for his parties.
Oh, yeah.
So for example, there's this famous story about him. He basically had you don't say photographic memory. How do you call it these days?
Photographic,
Any
eidetic,
Eidetic. Anyway, so a friend of his, tells a story where he claimed to have this amazing memory. So to test him out, he asked him to recite the chapters of Between Two Cities, which he read like when he was a youth. And he basically started reciting it, and he asked him to stop after something like 10 or 15 minutes.
Yeah, I have seen that story reproduced a few times in slightly different contexts. But I think it's really clear that John von Neumann may have been the smartest person ever to have been born. And easily comparable to somebody like Einstein or James Clerk Maxwell or someone like that. He had this uncanny ability to switch disciplines and still be an expert. So he was deeply involved with quantum mechanics in the early days. He was deeply involved with the Manhattan Project. He was the only person on the Manhattan Project who was allowed to leave and come back and leave and come back at will. He could go anywhere he needed to go because all the other parts of the military needed his advice. He was deeply involved with ballistics. He was deeply involved with the shock waves of explosions. He was running the computers at Manhattan on the Manhattan Project. He went out and looked at other ways of doing the computations. Didn't find a good one. Still stuck with the IBM punch card approach, but managed to get the initial models of the implosion of the plutonium core to work. The guy was just a remarkable guy and lucky as hell until the end of his life. Lucky as hell because he managed to leave Germany a year before it became impossible to leave Germany. He joined the Princeton Institute. Right? He was the guy who brought a lot of other guys over from Germany saying, hey, it's nice over here in the U.S. You could come to Princeton. Oh, Einstein, come on over here. People like that. So he was a massive recruiter. And like you said, it's unusual to find a guy who is supreme intellect, who has supreme intellect, and yet really good social skills. And he did. He was a social animal. So very
kind of like
character.
Feynman.
Like Feynman. Yes, a lot like Feynman.
The funny thing about him, you talked about how some of these characters were kind of flawed, was that while he was such a great, amazing person and made so many contributions, he was also wrecked with self-doubt, and he felt that he hadn't achieved as much as his colleagues.
What's the name of that syndrome? That's got a name. I can't remember what the name of it is.
Imposter syndrome?
Kind of the other way around, right? It's like
he
You don't
basically
think you've
thought,
done enough, right?
yeah, he
You
thought that
haven't
he would like, obviously everybody knew what Einstein would be remembered for, and they knew what Hilbert would be remembered for, and he thought that he would not be remembered.
Well, he was remembered, and fondly.
Yeah.
He was one of the inventors of Monte Carlo, the Monte Carlo method. And the story there is fascinating. They were trying to figure out, how to model the diffusion of neutrons through a plutonium core. Right? How do you model it? How do you calculate that? And his buddy, whose name escapes me at the moment, his buddy sat down and said, "Well, how would you determine the probability of winning at solitaire?" Now, you could do that mathematically, or you could play 100 games and count the number of ones that you won. And that was the beginning of Monte Carlo analysis, which plays a huge role in the rest of the book. It drives the whole notion of Monte Carlo analysis, drives nuclear physics for a good long time, but it also drives the creation of object-oriented programming. It was Christian Nygaard's thing. He was a Monte Carlo analyst. And because of that, he started thinking about simulation and how to do simulation well. And of course, then you bring in computers, and he wanted to create the Monte Carlo compiler. And he recruited his buddy Ola Johan Dahl, and wrote this thing that they initially called the Monte Carlo compiler. It eventually became called Simula. And in the midst of all that, they literally invented object-oriented programming.
And in the context of JavaScript, because this is JavaScript Jabber, I think JavaScript borrows from self, and as I recall, self
Correct.
borrows from Simula.
Yeah, well, there's definitely something to that. The story that I have heard, and I don't know that this is absolutely correct, but the story I've heard about JavaScript is that it was Brendan Eich's task to create a language that would run in the browser. This is back in the Netscape days, the Mozilla days. And he wanted to make it Lisp. But he didn't have time, and there was self there, and he kind of borrowed from that and cobbled together this thing called JavaScript. That may be an urban legend. I think I've seen that once or twice in various threads on the web. I don't know if that's true at all, but I think it's funny.
If you want to hear the full deal from the horse's mouth, we have an episode where we had Brendan.
Oh, with Brendan Eich?
Yeah. And
Oh, beautiful.
Yeah.
Oh, beautiful.
I also conversed with him about this online, even though I wasn't yet with the podcast when you recorded that episode with him. It's first of all, it's not exactly that. He was toying with the concept, with the possibility of putting Scheme in the browser, but it never really matured. And yes, he did create and implement JavaScript in 10 days, which are fondly known in the community as the 10 days of glory. But he said that JavaScript in a lot of ways is more influenced by awk than it is by Scheme.
Okay.
For those of you who don't
Inline
know, awk is
tool.
kind of like Perl. It's a language for text processing.
Aho, somebody in Kernahan.
Correct.
Who's the W?
I forget.
I can't remember who the W is.
It's one of those
Remember.
Unix utilities that
Yeah.
you can pipe stuff in and pipe stuff out.
It's a
And
predecessor of Perl.
yeah,
Which
exactly.
is a predecessor of Ruby.
Yeah.
Is
Awk
it?
is cool. Actually, I think it's a cool tool anyway.
By the way, the very first wiki ever put on the internet was a couple of hundred lines of Perl written by Ward Cunningham in the very late 90s. Just,
Well, CGI scripts. People don't remember the origins of the web, but the initial web servers were mostly done in Perl because people didn't want to do all that text processing in C.
So I have another question. I'm going to change this topic a little bit because, we talked about how computers were initially kind of these calculating machines. And if you go watch like the Hidden Figures movie, right? They have these women that are called computers, and their job was to do the math, right? And then they got this fancy computer that would do the math, right? And so then they were programming the computer. But when did computers kind of go from this math machine to this sort of general purpose machine that we kind of think of as a computer today?
That's a really interesting question. And there's two ways to look at that. You could look at it from the practical point of view. When did computers start doing more than just math? When did they really start doing more than just math? And the guy who comes to mind there is Dijkstra. Because Dijkstra was the guy who was playing with graph theory. He came up with this clever way of computing the best route to go from one city in Norway to another, something like that. And it was a demonstration. He wanted to show this demonstration to his superiors. And he came up with this algorithm to do that. And that's a very different kind of problem than computing the implosion wave in a plutonium core. So that was a more practical one. So from that point of view, you could lay this at Dijkstra's door, and that would have been late 50s. Maybe the early 60s, but probably the probably the mid 50s, actually. But it was Babbage in his contemplations of his analytical engine, the thing that never got built, right? Who started toying around with the idea that this machine that he had in his mind that had 1,000 registers and a mill that could add, subtract, multiply, and divide, and a mechanical bus that could move numbers from registers to the mill and back again, right? And was programmable by punched pieces of wood, Jacquard loom style, right? And these big chunks of wood with holes drilled in was how you would punish them. And that's how you'd program them, punish them. Good word, Bob. That's how you would program them. And in the midst of just thinking about this machine, Babbage starts realizing that you could write a program for this machine that could play chess. He started working that out. Right? So in that sense, Babbage is the first guy to cross that boundary, to get out of the mathematical world and into the symbolic, abstract world. And he had a number of other ideas like that. He actually put together a machine that could play tic-tac-toe. He actually built that one. Knots and crosses, although, simple machine to build. Still, he was probably the guy that first had that concept.
That's amazing. I didn't consider that. Yeah. There are several people that you decided not to include in your book. A few that come to mind are Donald Knuth or Church. If we're looking more recently, maybe somebody like Linus Torvalds. So how did you decide to leave certain people out?
Those are not conscious decisions. I did not have a list of people to leave out. What I did have was a hard cutoff date. I wanted it to be a history book about other people right through the late 60s into the early 70s. And then from that point, that's where part 2 of the book begins. Then it starts to become autobiographical. From that point on, I can relate what was happening in the industry as an eyewitness, as a participant. So I shifted gears entirely and just started talking about my experiences through the next 30 years, 30 or 40, whatever it is, some number of years. And I described the industry from an insider's point of view at that point. So the hard cutoff date was one of the reasons that I didn't put Linus in there, for example. People have complained a lot that I should have put Margaret Hamilton in there, right? And I would have loved to. I actually bought a whole bunch of books on the Apollo program to read about that. But it turns out there's not a lot written deeply about the stories there. Or if there is, I missed them. So, I went to look for that, but didn't find it. Limited amount of time. I thought, okay, I can probably skip that one. There's a number of other people that I should have written about if I'd had the space, like John McCarthy. I would have loved to have told an in-depth story of Lisp. That would have been a great story to tell. just ran out of time, ran out of materials. And so,
Engelbert and the mother of all demos.
I'm sorry,
Engelbert and the mother of all demos.
that's a story I don't know.
Check out the video for the mother of all demos. Basically, you can find it on YouTube. Let me do a quick search.
The mother of all demos. Sounds good.
Yeah, it's still considered to be the greatest demo of all time.
It's like I see a couple of them here. One of them's like an hour and 40 minutes.
Yeah, it's pretty long. Basically, while everybody was doing punch cards, so this happened. Let me do it. I'm looking at Wikipedia. It happened in '68. So everybody was still doing punch card. This guy comes along and does, well, he was a professor. He does a demo. I think he was a professor, a 90-minute demo, live demonstration, showing stuff like Windows, a mouse, drag and drop, copy paste, hyperlinks. 68.
Yeah, well, okay. That's where Alan Kay got the idea, huh?
It's pretty nuts. And he does this in this kind of deadpan voice. And he's wearing a suit and tie, and he didn't do it for it wasn't like a CEO talking up there. This is like academics talking about stuff. So I highly recommend for our listeners to, or for you, if you're not familiar with it, to go to YouTube and just search for the mother of all demos and watch the video. It's pretty
I put a
amazing.
link into the live
Sounds
stream
great.
chat.
So you said that the second half is kind of autobiographical. When did you enter the industry?
I got my first job as a programmer at age, I think it was either 16 or 17. I can't remember exactly. And it was a summer job, and it was very temporary. And my father had actually gone to this company, who was just a few miles down the road, and walked in there and said, "You will hire my son." That was the kind of person my father was. And I found myself working at this place. And it was like 2 or 3 weeks that I was there, and I wrote a little bit of assembly language under the watchful eye of my supervisor. Got one little program working, and then he said, "Well, thank you very much, Bob, and now your time here is done."
When was that, if I might ask?
I think I was 16. That would have been, I was born in 52, so that would have been 68-ish, something like that. I went back to that company like a year and a half later, and for a while I operated offline printers, printing junk mail on third shift, and then rapidly became a programmer. I think I spent about 6 months doing the offline printers, but knew some guys who were programmers and talked to them and convinced them that I probably could be writing code. And from that point, I was writing a little bit of COBOL, which I hated. And then from then on, it was mini computer assembly language, and a lot of it. So that's when I got my start. So I guess you'd have to say, really, my career began in the very, very early 1970, maybe late 69.
And did you also go to university or college or something?
Oh, no. This was like the Vietnam War era, and the universities were all going nuts. And my family wasn't really very well off. And in the meantime, I had devoured books on COBOL and PL1 and Fortran and PDP-8 assembly language. I was a real computer nerd. Still am.
So you're the original self-taught developer.
Well, probably not. One of them, I mean, self-taught. Grace Hopper was self-taught. But one of
but she did come from academia, I believe.
She did, yeah. She was a mathematics professor. Yeah, at I can't think, Vassar. I can't remember.
Look, I have to say that today CS departments are departments on their own. But when I studied in the university, the CS department did not exist. It was part of the math department.
Yeah, I mean,
it only came into existence a couple of years later.
Yeah,
There
as
weren't
children
any
like
independent
me,
computer
there
people.
was
science
a CS
courses.
department when I went to college.
If you wanted to be a programmer in 1969, there weren't a lot of courses you could take, and access to computers was very difficult. And that was one of the problems that Kemeny was trying to solve. Kemeny was at, one of the colleges out there. I can't remember where it is, on the East Coast. And, access to computers was a really big problem. They eventually got time on one of the computers at MIT, and they would do it by schlepping punched cards several miles. One of the guys would get on a train and haul punch cards up there and run the jobs and then come back with the listings. And so if you were a student, you would submit a program and maybe a week later you got a listing. And Kemeny wanted to solve that problem. And he bought a little mini computer. It was a really dinky little thing. And maybe he had 6 students that really learned how to do it very well. And then it occurred to him that he needed a bigger machine. And he wrangled General Electric to give him, for a very, very low price, a couple of big honkin' GE machines. I actually worked on a machine like that at about that time, at that same company, General Electric Datanet 30. Really big in those days, big machines. And he and his buddy and a few undergrads wrote in assembly language a time-sharing system and a basic compiler in about 6 months, and turned the student body loose. They had a whole bunch of teletypes that they just scattered around the school, Dartmouth. They scattered around Dartmouth. And the students could suddenly find themselves writing code and seeing it execute in the same session within minutes. And what did the students do? They wrote games.
Well, and you did bring up the fact that Ritchie and Thompson and Ritchie created Unix in C because they wanted to play games.
They play Space War.
Yeah. By the way, one of the things that I'm really sad about is I remember in the 90s or something, get a copy of the IEEE Spectrum magazine talking about the origins of the video game industry, Atari and whatnot. And unfortunately, I did not keep it.
Oh,
And
yeah.
some crazy stories there as well. I mean, the original Ataris had 1K of RAM, which, think about that the next time you're writing your 5 megabyte, your 30 megabyte web application that does absolutely nothing.
Or you play
They wrote Space
on
Invaders in
emulator.
1K.
You got a bunch of guys out there on the net going, "Okay, boomer."
I don't deny it.
I remember playing games on the Atari. I mean, I was like 6, but
Well, I can tell you a funny story is that the device was limited to 4 colors. And one of the games, they wanted to have 8 colors. So they want to have 4 different colors at the top and 4 different colors at the bottom. So what they did is they actually synchronized the game loop with the television refresh, and they would switch the palette of the colors mid screen.
oh wow.
So that way they could get 4 different colors at the 2 halves of the upper part of the screen and the lower part of the screen.
There was a lot of that kind of shenanigans going on.
I love video game podcasts, like and the YouTube channels like Modern Vintage Gamer and Video Game Historian doesn't really do much anymore, but the stuff that's there is great. I love learning about all those tricks. I think Modern Vintage Gamer just did one on, I think it was the Nintendo that does that where they're doing that, where they're swapping on the chip, they're swapping what's being presented to the thing that's reading it in real time with a little microprocessor so that they can get 2 color palettes.
Yeah. They can't afford the garbage collection in the middle of their loop.
It's all written in assembly language.
All right. Well, I've
Jump
got a
Well,
hard stop
go-tos
coming up in
everywhere.
10 minutes. So
Yeah, just as an interesting aside, we mentioned Lisp. Lisp in the I believe 50s or 60s, I think, introduced the concept of garbage collection.
Yeah, that's true. Yeah, Nygaard and Dahl needed garbage collection in their Monte Carlo compiler, and they tried to write their own, and then eventually they bailed out and borrowed McCarthy's, the concept of McCarthy's garbage collector, and that's what they put into Simula for a while.
all right, I'm going to push us to picks because I've got to go. I have a call in 10 minutes.
Okay,
I could talk history forever.
I know, right?
I know it's the glory days.
We'll get
right?
Bob back when Clean Coders comes out. We'll see if we can get him on Ruby Rogues and go into more of this stuff. But yeah, let's do picks and let's be fast because I want to be able to do them. So AJ, you want to start us with picks?
Yeah, I'll just pick a short one. No, I can't do that. But The Expanse, I finished book 2, and I just have to say, so far, between book 1 and book 2, the book is like the book and the TV show are very, very, very similar.
Mhm.
If I were to describe the plot of them, they're pretty much identical. But the book is so much better because in the TV show, they cut out like critically important elements that are absolutely essential for you to understand why they transitioned from what seemed like two completely different TV shows with the same actors between season 1 and season 2, where it's like, okay, these are not related other than it's the same people. There's like a few key pieces that if you know, it's like, oh, okay, now I can have suspension of disbelief again. And then likewise, there's so much stuff that they added into the TV show that's completely irrelevant and just draws out like a couple extra episodes. Man, yeah. So if The Expanse didn't hit for you on the TV show, but you like the first season, and you want to know where it goes, I think the books are better. Chuck, you'll have to chime in to, if is the ending satisfying after, what is it, 6 books or 9 books or something?
But they don't do all the books in the TV series. So just
yeah, I think they cut out pretty early.
The books are very, very good, way better than the TV shows. I had the benefit of having read the books before I watched the TV show. Also, fair warning, there's a little bit of a gap because the sci-fi folks dropped the show and then Amazon Prime picked it up. And so there was like a year where they didn't record. But yeah, anyway, the TV show is terrific, but the books are, and yes, they do stay pretty close to the books. So yeah.
So to keep things short, that's all I'll pick today. Is just I got finished with that book and I liked it. And I do have to say, Avalasara is worse in the book than in the TV show. Previously, I complained all she does in the TV show was come in, say the F word a couple of times, and leave. Yeah, she's the same in the book.
Like better as the books go on.
Okay.
Dan, what are your picks?
Yeah, so I called dibs actually on this pick when it came along, because it's so great and it's kind of related to some of the stuff we'll be talking about today. So it turns out that this guy called Dimitri Mitropoulos, I hope I pronounce his name correctly, implemented the game Doom in the TypeScript type system. Because as we all know, the TypeScript type system is Turing complete. It's effectively a dialect of Lisp, I think, in a certain way, because you can implement loops with recursion, and you also do case if statements, along these lines. So he basically managed to implement something like a compiler that something that takes, I think, LLVM code and basically translates it into TypeScript types. It took him all of a year of working 10-hour days to implement. And I think he has it running at something like a frame a week. But it works, and it's the most insane thing I've ever seen. He put a video up. He said he'll put two more. One that he talks about, he'll go into the details of how he actually implemented it, and I'm really trying to get him to come on the show.
Oh, that would be
If you're listening, please do. I've reached out to him, and I hope that I'll be successful. He did something like there's something like a trillion types in the code, something like that. He had to remove all the limits out of the TypeScript compiler source code.
oh, y'all.
Okay.
Wow. I wish I had copious
That's
amounts
a
of
really
time.
worthwhile project.
Yeah.
You
Was
know,
this
It's going to change humanity.
this was very different from the Floppy Bird implementation? Yeah,
Well,
because Floppy Bird was an interpreter, and this is LLVM.
yeah, something along. If I understood correctly, like I said, we really need to get him on the show. But the funny thing though, we talk about is the fact that the type system in certain programming languages, TypeScript, also kind of C++ comes to mind. I think even Java to an extent is effectively a Turing complete programming language in and of its own, because you can implement recursion and with halting conditions. So,
Cool.
yeah, it's pretty nuts.
All right.
Anyway, you can't top that, and that would be my pick for today.
I cannot top that. I'm going to throw out two picks really quick. I'm going to do a card game. I've picked it before. I've picked it recently, but it's the one that I've been playing the most lately. It is The Gang, and it's basically cooperative Texas Hold'em poker. And so what you all get dealt your pocket cards. You do, you flip the river and the flip and the flop, right? And at each stage in the game, there are chips for each. There's one for each player. One up to however many there are. Whoever thinks they have the winning hand will grab the top one, right? Sometimes you fight over the chips. And then, you go around, and eventually once you settle on the chips, then you do the flop or the river, and so you get three more cards, and then, right. And so then the chips change hands because, right, now you have a pair or two pair or three of a kind or whatever. And anyway, it's super fun. So, it takes about 20 minutes to play a game. I've played it with 4 and 5 people. It gets a little harder when there are more people, but it's totally fun. So I'm going to pick that. And then the other one is I've been watching the latest season of Reacher. I watch a lot of these kind of action kind of shows. I really enjoy them. I have to say the plots aren't always that creative, right? They have a lot of the same
They're not
elements to them.
supposed to be.
But I can just sit and veg and turn my brain off. So anyway, I'm enjoying that. There are like 4 episodes out now. So Reacher on Amazon Prime. Bob, what are your picks?
In the spirit of ancient history, there are a couple of science fiction books that are worthy of a good solid read, even though they're very old. The books that come to mind, they're 100 years old, are When Worlds Collide and the sequel, After Worlds Collide. And don't get confused by Velikovsky's Worlds in Collision. That's not the books that I'm talking about. When Worlds Collide and After Worlds Collide. Wonderful stories written in the 1920s about an astronomical collision with the planet Earth and the way the scientists of the age find a way to survive. But I won't go any further than that, except to say that it's very colorful and lovely and wonderful science fiction if you can tolerate the glaring scientific errors that would have been obvious in the 1920s.
Awesome. Can you do spoilers after 100 years? I guess maybe you could. Anyway, Bob, if people want to find you on the internet or connect with you, where do they find you?
Cleancoder.com. That's my website. CleanCoder.com. You can go there. Twitter handle is Uncle Bob Martin. Beware. And other than that, I'm just around.
All right, good deal. Well, thanks for coming, Bob. This was fun.
My pleasure always.
This was awesome. Thank you so much.
All right, we're going to wrap it up. Till next time, folks. Max out.